And here's the part that stings even more. When that microwave was at its hottest, the creatures sitting at the top of many ecosystems weren't mammals at all. They were reptiles, in a world we affectionately call the Age of Mammals. Names lie, variables don't. In this entire episode, I'm not going to play the game of who's the biggest and baddest. I want to help you understand a set of things that actually determine fate. Metabolic type, body proportions, position in the food chain, daily calorie requirements, and what you rely on to survive. Because in extreme heat, the ones that survive aren't the strongest. They're the ones that fit best. But before we can talk about those variables, we need to smash two widespread misunderstandings. First misconception: the Cenozoic was just one long, dreary cold spell. Our default mental picture is that the Mesozoic was hot and muggy, dinosaur territory. And then once the dinosaurs were gone, the world gradually cooled down, slid into ice ages, and the whole scene felt like an empty theater after the show. That narrative is smooth, but half of it is wrong. Ice ages were just interludes. Wedged between them were several extreme heat spikes, and the most intense one was so hot that it ranks among the hottest moments in Earth's entire history, turning the planet into an overgrown jungle and swamp mess that weirdly echoed the bizarre Carboniferous period 300 million years earlier. Second misconception: the dinosaurs died and modern mammals just naturally took over. That compresses the timeline way too aggressively. To understand this, we have to go back to the end of the Cretaceous. The asteroid did cause a catastrophe and a short-term global chill. The planet eventually climbed back to a warmth comparable to the Cretaceous. There were no permanent polar ice caps. CO levels were far higher than today. The ecological niches were open, but the mammals that stepped in during the Paleocene were mostly small, and the forests were dominated by just a few tree species. The asteroid kicked the door open. It didn't decide who moved the furniture in or how it got arranged. The one that actually rearranged the room was a sudden spike in temperature, about 55.8 million years ago. You see a long, gentle uphill stretch, and then, out of nowhere, an ugly spike jutting out like a finger poking through the page. These rapid global warming events are called hyperthermals, and the PETM was the nastiest spike of the entire Cenozoic. What makes it even more ridiculous is that the starting line was already hot. Before the event, global average temperatures may have been around 28.3 degrees C, about 40% hotter than today. Then the PETM floored it, pushing global temperatures up by another 8 degrees C. To feel that number in your bones, since the Industrial Revolution, humanity has cranked the planet up by about 1.4 degrees C, and we're already seeing major problems. 8 degrees is on a completely different level. At its peak, the global average might have hit about 34.5 degrees C, hotter than the hottest country on Earth today. Even the high-latitude Arctic seas were as warm as today's subtropics. In other words, if you went to Antarctica back then, you'd better have packed swim trunks and sunscreen. And this wasn't a heat wave that lasted a few decades. It stuck around for about 200,000 years, roughly 20 times longer than the last glacial maximum. In just a few thousand years, the peak of the Ice Age reshaped half the planet. Imagine what 200,000 years of sustained heat could do. So what pulled the trigger? Here I have to be honest. There's no consensus. We know CO shot up from about 1,000 ppm to over 2,000, more than 4 times today's levels. That kind of spike can't be explained by the normal carbon cycle. Something must have injected a massive slug of carbon into the atmosphere. But what that something was is still an open case. Volcanoes, underground peat fires, ocean circulation changes, even comet impacts have all been proposed. Some have even half-jokingly blamed animal respiration. The fossil record hasn't given us the full story. What we do know for sure is that the heat wave came with a side effect: more moisture. Evaporation and rainfall both skyrocketed, supercharging the already abundant forests. Tropical rainforests spread into what's now arid Texas. Palm trees grew in the Arctic. Even azolla ferns, aquatic plants, floated around the poles. None of those grow there today. The whole planet was turned into an over-microwaved jungle and swamp hybrid. All right, stage set. Now let's talk about the real core variable. Why did some groups shrink under the same heat while others exploded? The master switch is metabolic type. Take warm-blooded animals. That's us mammals. Being warm-blooded means you can regulate your own temperature, but it also means you generate heat internally and are prone to overheating. When temperatures hit PETM levels, mammals responded in a counterintuitive way, not by bulking up to tough it out, but by shrinking. Smaller bodies mean more surface area per unit of body mass, which makes it easier to dump heat. What's really driving this is an energy balance sheet. Warm-blooded means high metabolism, which means you need a constant stream of fuel to keep the internal furnace running. The hotter it gets, the harder it is to shed that internal heat. Shrinking your body both cools you down and cuts your energy bill. And there was a side effect. Dwarfism pushed populations into smaller, more isolated niches, accelerating speciation. It's thought that this wave of dwarfing is exactly what gave rise to many of today's major lineages. Artiodactyls even towed ungulates like giraffes, bison, and even whales' distant relatives. Perissodactyls odd-toed ungulates, like horses, rhinos, and tapirs, and the earliest proto-primates, like Purgatorius. In other words, your own lineage was largely baked into existence by that microwave. Now, look at the cold-blooded side, and the direction flips completely. Reptiles rely on external heat. When the environment warms up, it's effectively free energy. They no longer have to budget for staying warm, so that surplus gets dumped into size and diversification. Many reptiles grew larger and more diverse, with some formations yielding over 100 species, and their position in the food chain climbed right along with them. Pull the lens back to the whole food web, and you'll see that the same variable reshuffled the entire deck. The main characters weren't one or two super monsters, it was the whole network. On land, there were hoofed crocodiles, scientifically known as Pristochampsidae. Don't let the name fool you. They didn't actually have hooves. Their blunt clawed feet just happened to resemble them, paired with long legs that let them run and hunt on land, while retaining the classic crocodile package, heavy body armor and jaws that could take a big chunk out of you. Picture a crocodile that could chase you down on land, and you get a sense of how intense life was under that microwave. In the oceans, there was the giant sea snake, Paleophis*, estimated at up to 12.3 meters long, one of the largest sea snakes ever. Plus fully marine crocodilomorphs, like the Dirasauridae, sporting long, thin, gar-like snouts, with some species reaching about 6 meters and thriving across marine, brackish, and freshwater environments. On the mammal side, mostly adorable miniatures. Early artiodactyls like Diacodexis were small enough to hold in one arm, often compared in size and build to modern chevrotains and duikers, though I should stress, those are size and build comparisons, not lifestyle assumptions. Early perissodactyls were slightly larger, about medium dog-sized. Interestingly, back then, rhinos, tapirs, and brontotheres all looked remarkably similar. Compact, four-legged, no horns, no flexible snouts, no battering ram skull bosses, just a bunch of stubby little runners. Horses were actually the most unchanged, with the biggest difference being their mini size. That small frame was a huge advantage during the PETM. Easier to keep cool, and easier to hide in dense brush. The truly relatively large mammals were the Pantodonta and Phenacodontidae *Berylambda* could reach pony size, about 650 kilograms, and could basically outsize most predators in its environment. Think of it as a herbivorous Godzilla. Now, about the predators, here I need to clear up another thicket of confusion, because paleontology names are a minefield. Oxyenidae means sharp hyenas, but they weren't hyenas. They looked more like otters and badgers, and walked on flat feet. Hyenodon also has hyena in its name, but again, not a hyena. It was named for its similarly shaped teeth, and its teeth were actually better suited for slicing flesh than crushing bones. Then there's *Viverravidae. asterisk literally meaning ancestors of viverids, except they're not actually related to modern civets and mongooses. The name stuck because they looked so similar that early paleontologists assumed they were ancestors. This is exactly the trap I keep warning you about. Looks like does not equal is related to. I'm only making clarifying comparisons here. I would never use modern relatives to reverse engineer the lifestyle of these ancient beasts, because that's a whole different pitfall. Let me lay out the evidence clearly so you do not think this is all guesswork. That ugly spike on the temperature curve shows it was a sudden event, not a gradual one. CO reconstructions show a jump from P.am pointing to an external carbon injection. Isotope and sediment records show forest belts expanding far beyond their usual ranges. Texas rainforests, Arctic palms, and Azolla ferns. The Wasatch Formation, spanning multiple U.S. states, is incredibly fossil-rich, yielding dozens of primate-like plesiotopiforms, early artiodactyls and perissodactyls, and several major predator groups, essentially giving us a window straight into that hot pot era. Among the predators, the most dangerous were probably the wolf-like mesonychids, Pachyina*, weighed up to about 396 kilograms. And tooth-wear patterns suggest bone made up a big chunk of its diet. Meanwhile, the arctocyanids didn't handle the heat well. They were in decline before the PETM even ended, driven directly or indirectly by the changing climate. Notice I'm not writing this as one single cause. It looks more like a tangled downhill path. Underwater, the script flipped completely. The land got supercharged by the heat, but the ocean took a beating. The PETM was actually more of an extinction event in the seas. Benthic foraminifera suffered losses even worse than during the KT impact. But the real killer wasn't the heat itself. It was the cascading effects: warmer seawater, stratification, and methane released from the seafloor all combined to turn the water anoxic. Especially in the North Atlantic Ocean, circulation patterns reversed, pumping warm water into the deep. On top of that, acidification dropped pH by about 0.46 units, cutting into the carbonate ions that marine organisms need to build shells and skeletons. This was a feedback loop, not a single switch. Even so, there were winners in the water. Sharks filled the gaps left by the KT extinction and expanded their ranges into Scandinavia, the UK, and even the poles, many of them looking remarkably similar to species alive today. A few, we should be glad, stayed in the past. Mackerel sharks like *Cretalumna, appendiculata*, and *Otodus obliquus*, with the latter reaching about 9 meters, very likely the largest animal of the entire PETM. Add those giant sea snakes and marine crocs, and you had to watch your back whether you were on land, in fresh water, or in the open ocean, and yes, that included the possibility of being chased down by a long-legged croc on shore. Oh, and the bugs. There were tons of them. The heat expanded their ranges, fueled their diversification, and probably spiked insect repellent prices. So what does all this teach us? Fate was never determined by who's biggest and baddest. It was about how metabolic type times body proportions times position in the food chain got reshuffled under extreme conditions. Warm-blooded animals were squeezed into smaller sizes, which ironically exploded into new lineages. Cold-blooded animals rode the warmth to dominance, sitting atop many ecosystems. The ones that rose weren't the strongest. They were the ones that fit best. So the name Age of Mammals is itself a kind of hindsight bias, at least based on current fossil evidence from the PETM's Western Hemisphere. Reptiles often still sat at the top of the food chain. Names lie, variables don't. Now pull the lens back to the present. The PETM took about 200,000 years to do its +8 degrees C. Humans are pushing +1.4 degrees C in just a few centuries. The scale is different, but the carbon-climate ecology chain is the same logic. And the heat didn't shut off like a switch. Silicate rock weathering locking carbon into stable molecules, plus organic carbon burial in sediments. slowly pulled CO back down. But even after that, the planet stayed warm, and before long, there was a sequel. The Eocene thermal maximum 2. Another spike. Both belong to the broader early Eocene climatic optimum, one of the most sustained hot intervals Earth has ever seen. But no matter how hot it got afterward, the PETM was the one that turned the dial the highest. Nothing since has topped it. And so the question hangs there. The fossil record has not given us the full story. What exactly pulled the trigger on the PETM in the first place? Why has nothing since been able to turn the dial that high again? If you were running that ancient microwave yourself, and metabolic type really does decide who sits at the top, then, the next time the planet flips, who would be sitting at the top of the table? Drop your bets in the comments, hit subscribe, and we'll keep digging next time.